Hello, everyone. Thanks for joining. I'm sure either some more people will still join later on, or you can watch it on YouTube afterwards. So I'm very happy to see some of you, I think, not only from Switzerland, but also from abroad. So that's nice. So yeah, thank you for being here at this seminar organized by the EPFL Space Center, the eSpace Center, with Dr. Andrew Wilson, who's going to talk about, but he can introduce it later on, about how one should integrate lifecycle engineering of space systems into concurrent design processes. So Dr. Andrew Wilson is at the moment a lecturer in environmental management at Glasgow Caledonian University. But he has really gained expertise in the field of space sustainability and in particular life cycle assessment. He did his PhD on how to not only do environmental life cycle assessment, but also social and the economical side of things. And from there on, you can find many very interesting papers that he published recently. But I think, yeah, Andrew, I think it's best that you present yourself and then present this interesting presentation that I'm looking forward to. So the floor is all yours.
Yeah, thanks, Marix, for the introduction. I hope everyone can understand me through the thick Scottish accent, because I know it's not always the easiest to understand. But yes, my name's Andrew. I've been working in this kind of field, space sustainability, for around a decade now, with a particular focus in life cycle assessment, and that is what I've got the pleasure of talking to you all about today, particularly about how we can use that to design more sustainable space missions. So the background to this, very simply, is that historically speaking, space technologies have, although have been playing a crucial role in achieving sustainable development, they actually haven't been bound by regulatory requirements from an environmental perspective to a very high degree. By that, what we mean is, for example, the Montreal Protocol, substances that deplete the ozone layer. Space was missed out, despite launchers being the only form of man-made pollution to actually inject ozone-destroying compounds directly into the stratosphere where the ozone layer resides. You've got at a European level the restriction of hazardous substances, the WEE for electronic waste legislation. Both of those grant exemptions to the space industry, and for that reason, the space sector haven't really needed to worry too much about the environmental impact at a sector-wide level. But in recent years, there has been this growing realization that space sustainability is essential, and that also needs to include Earth-based impacts, as well as just space debris and orbital space depletion. Now, in that regard, when we're looking at how we kind of quantify that, it's absolutely essential that we have the right tools there, and that they can be based on evidence that we can scientifically back up any environmental claims made. And that's very important given recent findings from the European Commission. So recent findings from a screening of websites exercise actually found that 42% of environmental claims made by company were either exaggerated, false, or deceptive, and could potentially be breaking commercial practices under EU rules. And that's not just confined to other sectors. The space sector is also equally guilty for this, and there's been a growing number of unsubstantiated claims that have been observed by us here in the UK, but also by the European Space Agency as well. So it's very important that if we're talking about green products or sustainable products, that we're actually able to put a number on that and actually be able to scientifically evidence what it is we're actually talking about. Now, in that regard, one of the best tools that was identified about 15 years ago now at the European Space Agency for doing this is life cycle assessment. So life cycle assessment, very simply, is an internationally standardized approach for quantifying the environmental impacts of a product, a process, or service over its entire life cycle. So this is everything from raw material extraction to the production and use, the transportation, the use, as I said, and the end of life. And it is standardized by the ISO 14040 and 14044 standards, which provides us with this framework for conducting the assessment. So it's very simply the goal and scope. So what is it you're looking to do and what is it you're looking to calculate? The inventory, which is the data collection and calculation phase. The impact assessment, where you kind of quantify what the results of your inventory analysis is in terms of to environmental media. So what are your impacts to global warming potential, to ozone depletion, water depletion, etc., etc. And then interpret those results. So what are the meaning of those results? So really, when we're thinking about life cycle assessment, we need to think it's a multi-step approach. So we're looking at it throughout its life cycle. So through the design, the production, the launch, the use, the end of life. We're looking at different criteria. So resource depletion, global warming, ozone depletion, acidification, toxicity. And we also need to think about it in terms of the function or the service provided. And that is very crucial if you're going to do a comparative assessment, if you want to compare two products. For example, it's not a fair comparison to compare a tin of paint with a snow globe, for example, because they don't provide the same service or function. It would only be fair to compare a tin of paint with another tin of paint, for example. Now, applying LCA to space is complicated, very complicated, because space is quite unique in comparison to other sectors. It has low production rates. It has very unique and specific impacts on the environment, such as ozone depletion from launch. It uses often specialized materials and industrial processes that are unique to specific missions, and it has very long development cycles. And what that essentially means is that traditional life cycle assessment tools don't have the capacity to actually calculate the environmental footprint in a very good manner. So there's a need here to develop dedicated data sets to enable us to calculate this for the space sector, and also methodological rules that we would follow to harmonize that approach. And luckily, the front runners of this work was the European Space Agency, and they, based on a number of studies they've run over the years on launchers, on spacecraft, and of the ground segment, created a new framework for Space LCA, and it consists of three components. So the ESA LCA handbook, the database, and the eco-design tool. And the idea behind this was really to address the specificities of the space sector by tailoring the methodological rules contained within those ISO standards to be more appropriate to the space sector without risking non-compliance with the ISO standards. It is, of course, still voluntary, but its application might allow industrial stakeholders to become fully transparent in their operations by scientifically quantifying the overall environmental impacts of their space products. So very quickly on these three segments, the Space System LCA guidelines, they essentially are the methodological rules that you should follow if you want to perform a Space LCA. They are designed to comply with the ISO 14044 and 40 standards, and they are currently available to European stakeholders upon request to the European Space Agency, but there is also in the background some product category rules being developed at a European level, which may eventually replace these guidelines. But if you want to know how to conduct a Space LCA, this is what you should be reading. In terms of the ESA LCA database, this was a database that the European Space Agency compiled to have a centralized location for life cycle data sets on space systems. And it's meant to facilitate the work of Europeans in working on space LCA, and it contains over 1,000 data sets. Just like the handbook, this is available on request. You will need to have a valid Ecoinvent license to obtain access to it, but again, that has been made available by the European Space Agency. And the last part of the framework is the Space Opera tool. So this really looks to integrate this into the design of space missions, particularly through concurrent engineering. Unfortunately, it doesn't actually work at the moment. There's a number of known bugs which were found during some tests, a couple of which I did at the European Space Agency. So that needs a little bit more funding, let's say, before it becomes available, which is somewhat problematic. But the question of the work that we did was, does this actually go far enough? So, we're focusing on the environment. Of course, it's a major area of concern. But when we talk about space sustainability, in the traditional sense of sustainability, that means environment, society, and economy. So we're missing out two very key elements here, which it really prevents it from being a full sustainability assessment. So what we proposed here was adapting that ISO LCA framework to also capture the social and economic elements. Now, the problem you have when you do that is, how do you handle these different elements? Do you see them as three standalone assessments? Do you integrate them into one assessment? So really key here is adding that additional step, which is called multi-criteria decision analysis, and that allows you to value the importance of each of those dimensions of sustainability and then interpret the meaning out of that. So what we essentially proposed was this new life cycle sustainability assessment framework for space. And I think what's key to remember here is, rather than being a model itself, this framework is this is really a framework of models, rather, which is designed to provide more relevant and transparent results in the context of sustainability and allow integrated decision making based on a life cycle perspective. Now, that's all well and good for calculating results, but one question which is quite key here is, when is it actually best to apply life cycle assessment or life cycle sustainability assessment? And very simply, it's always best to apply it as early into the design as possible. And the reason for that, as we can see in this graph, is that as we kind of go forward in time, the level of a space mission in terms of its definition will increase. But almost in parallel, the potential modification decreases. And that is because as we define the space mission more and more, the components, if you like, get kind of locked in. So modifications are harder to actually achieve. And in parallel with that as well, the impact of making an eco-design decision will also increase. So what we mean by that is, as you go through time, if you implement an eco-design choice, because a lot of the components are already locked in the system, your impact of that change will be smaller than if you implemented it earlier, where you have more room to reconfigure the design, if you like. Now, when we talk about space mission design and applying it early, one approach which is extremely novel and really upcoming, in my opinion, is concurrent engineering. And concurrent engineering is essentially a systematic method of designing and developing products where different activities are run simultaneously. And what that enables is us to decrease production time and also reduce costs. The method is not essential practice within the space industry, but it's become quite a well-established means for developing early space mission design concepts, particularly Phase 0A feasibility studies. And for this reason, applying life cycle assessment or life cycle sustainability assessment within the concurrent engineering process has a good potential to act as a first step for the space sector to mitigate potential life cycle sustainability impacts and design more sustainable space missions. And really that's because the approach can be integrated into the decision-making process from that very early stage. So you're identifying potential hotspots. So those are areas where there is particular impact, either environmentally, socially, or economically, and thereby suggesting approaches to assist in remediating those impacts. So the key elements really to concurrent engineering is, you need of course, a facility. So that is a room, for example, to actually conduct the concurrent design session. You need a team. The team needs to be multidisciplinary and capable of designing a space mission. So you'll have experts there from different disciplines such as thermal, you'll have systems, you'll have propulsion, so on and so forth. The team needs to communicate with each other to collaboratively design this thing. And of course, to do that, you need domain-specific software or hardware, and you also need a centralized design tool. So to just give you some examples on some of those elements, at the University of Strathclyde, we have a concurrent design facility. It's the only one in Scotland. This slide's probably a little out of date now, but the general ideas are there. So there's 18 workstations. They both have Linux and Windows operating systems hosted on an Ubuntu server. It uses several different centralized design tools. So originally we had the Open Concurrent Design Tool, or OCDT. That was created for the European Space Agency. We then moved on to Rhea Group's Concurrent Design and Engineering Platform 4, or CDP4, and then subsequently changed over to their upgraded version of that tool, which is called Comet, the Concurrent Model-Based Engineering Tool. We can see in the bottom right just a kind of a photograph of the room. So each workstation there has video and audio connected. You can share video, you can share your audio to the room. There's cameras, webcams at each station, microphones. And I would say one more thing is that it's actually going to be upgraded in the next few years as well. So if anyone's interested to see how that will develop, there's also a paper which you can find on my either ResearchGate profile or Google Scholar or wherever else. This is some examples of some concurrent engineering studies that I've been involved in the past. So the top left was one at the European Space Agency. So that was one of the first concurrent engineering challenges which took place. And I went over there specifically to test the Space Opera eco-design tool, which was a real challenge in itself. It actually ended up crashing the STech server. So it wasn't a fruitful endeavor, that's for sure. And the kind of the four photos on the right were some missions designed in the Concurrent and Collaborative Design Studio at the University of Strathclyde. The missions we'll talk about a little later. And then the one in the bottom left is quite an interesting one. So that was another one that we designed at the University of Strathclyde, but because of COVID, it pushed the design session online. And up until that point, concurrent engineering had never happened remotely before. So it was a very interesting study to see how that would work without the physical presence of a concurrent design facility. Again, there's a paper on that if anyone is interested. And an example of a design tool, Comet. So this is Rhea Group's concurrent design tool in the CCDS, which is a concurrent and collaborative design studio at Strathclyde. It eventually replaced the OCDT and CDP4. It's designed essentially to enable model-based systems engineering, particularly concurrent engineering. And what it does is it allows for different disciplines to share data. So essentially you can commit data to this central repository. So you can push and pull from a central server. You can set up specific parameters for your subsystem. So for example, if I was designing, say, a thruster, I might want to know the height, the length, the mass, for example. I might want to also add a mass margin. I can assign all these parameters in that model. I'll input the values and I can push that up to the server so everyone in the room can see those values. Now, talking about terminology, there are different life cycle principles that can be applied in current engineering. So we've talked about life cycle assessment, and just to go over that again, that really aims to look at environmental impacts of products, processes, and services. But the key is that it looks to assess those impacts. On the other hand, eco-design looks to go that one step further. So it looks to actually not just assess those impacts, but actually improve the environmental performance of a product, process, or service. And it does that at the design stage. Look at taking a life cycle approach. But it does that in a way that looks at trying to minimize any adverse impact on the quality or performance of that product. And for 2 decades, that was actually internationally standardized as well. But recently, in the last year or so, that was actually withdrawn without a superseding document. But many of the principles from that ISO standard, so it was ISO 14062, is enshrined in European Parliament and directives, essentially. So there's one here that establishes a framework for eco-design requirements in energy-related products, for example. Now, in comparison with eco-design, we also have life cycle engineering, which is the basis for the talk today. The only real difference between eco-design and life cycle engineering is very simply that life cycle engineering doesn't just look at environmental impacts, it also looks at social and economic as well. So again, it looks at that at an early design stage, looking at impacts across the entire life cycle with an aim of trying to reduce them as far as practically possible without compromising technical aspects. So this here is a kind of diagram of what I've just said. So again, the method is really applied in situations where sustainability coincides with design and production engineering. And within the production process, it allows decision makers to address significant adverse impacts without compromising those technical aspects. So you come to an assessment, and then it's a case of how do I improve that? So because of that, it makes it particularly well suited to concurrent engineering sessions of early space mission design concepts. There are many benefits of applying eco-design or life cycle engineering. These are just some of many, many, many more. So, of course, firstly is facilitating technology development. Of course, the space sector is at it's the cutting edge of technological innovation, let's say. So again, applying this can help lead with that and also move with the time. So as customers are becoming more environmentally conscious, it can also help you comply with current and also future legislation. So making sure that you are complying with minimum environmental standards or even going beyond those standards potentially as well. It can also help you cut costs. So if you look at particularly energy efficiency savings, you can also help reduce bottom line cost. And that money can either be reinvested back into the company, used for further eco-design measures or whatever the company wants to do with it. It can also create a better quality of life. It can create competitive advantages. I think for SMEs, one really good benefit is if you align with your staff beliefs, it helps you retain staff as well. But generally, it is, at least in my opinion, the morally right thing to do. Now, in terms of implementing this approach, how we have implemented this in some of the case studies we'll go on to show you is through the Strathclyde Space Systems Database, or the SSSD. The SSSD was developed by myself when I was at the University of Strathclyde, and it was designed with 3 main objectives in mind. So the first one was to fill the gap between the lack of LCA database, which ESA at that point hadn't released yet. It was to also advance the Space LCA methodology towards life cycle sustainability assessment. And then lastly, it was also to then integrate that into the concurrent engineering process for the first time through life cycle engineering. It's the point of the SSSD was never to compete with ESA LCA database. It was merely to complement it, let's say, and eventually there may be an integration of the two at some point in the future. And now that I am no longer at Strathclyde, it is managed by my company Metasat UK. It was validated at the European Space Agency in late 2018. It consists of, the last count we did was about 300 data sets. It might be nearer about 500 now. And it's built on top of Ecoinvent and ELCD databases. It calculates impacts at midpoint level, which is a problem-orientated approach. It translates essentially life cycle impacts into themes like climate change, ozone depletion, social performance costs, And then we also include what's called multi-criteria decision analysis, or MCDA, which we discussed previously, to try and understand the criticality of each social dimension and come to a single score. And the whole point was the SSSD was developed to align closely with a variety of international standards and norms. So just some of them, for example, are the ISO LCA standards, the ESA LCA framework, and also the LCA framework we showed you in one of the previous slides. This is just a visual example of how this works. So, you know, the goal and scope would be defined by the decision makers or the customer of the concurrent engineering study, and the Strathclyde Space Systems database would provide a lot of data sets as part of the inventory and also the impact assessment methods. Based on that, we can calculate the impact and run it through multi-criteria decision analysis to come to a decision, and then find the meaning of that through interpretation. This is just another example of how that works. So you've got your different inventories, so your environmental, social, and costing one. You characterize your results to find the amount of impact according to different impact categories here. You can then normalize them, which means kind of comparing them to norms, if you like, or benchmarking is another word you could use to describe it. And that converts the results into European equivalents for all impact categories. You can then weight them. We use the GRC, the Joint Research Centre meta weighting factors. That kind of adds an importance on what impact categories should be addressed at a European level. And that can then be used to come to a single score for the environment, society, and economy. And then to essentially use multi-criteria decision analysis, we add a second weighting, and that weighting was developed based on the number of SDG targets and indicators that were assigned to each of those three dimensions of sustainability. So that then can be used to come to a single sustainability score. Now, one thing I want to press on you at the minute is, when you make improvements to a system, it doesn't mean that you've developed something green. I like to use the word greener rather than green, because what is a green space system? You know, there's no definition to what that is. And it's important to recognize here that any man-made product is going to have some sort of inherent sustainability impact. So in terms of how it works within concurrent engineering, you have your different activities, concurrent engineering activities here. That will feed into the design of a spacecraft. We can then use that design to calculate the environmental impact of the design, the social impact of the design, and also the costing impact of the design. We run that through multi-criteria decision analysis to come to this single score. And once we've got that, we can feed that back in to the design model, and the people who are designing the space mission can then use those results to reiterate the design. Now, there are issues with regards to the application of life cycle engineering. Of course, the novelty of the approach, because up until we started looking into this at Strathclyde, there was really nothing being done on it. There was a handful of studies that have been conducted. Again, they weren't really in the public domain. There's inexperience and unfamiliarity with the concept within industry, and there's essentially no data that could have been used as a benchmark. So what we decided to do was we used some results, if you like, from some previous concurrent engineering studies that we conducted, that we had applied the life cycle engineering approach. And what we're going to kind of talk about now is really the results of that process, but also the technical and procedural elements that had to happen to enable that process, and also how the participants' behaviours and attitudes towards the approach evolved as we progressed through time. So these results, I would just say are relevant for 3 phase A's or phase 0A rather, small sat missions that were designed in the CCDS at the University of Strathclyde over a period of 3 years. So these are the 3 missions. So we've got MEOS, NEOCORE, and StrathCube. MEOS stands for Moon Ice Observation Satellite. MEOS also means month, or less frequently moon, in Scottish Gaelic. And as I say, these were designed between 2017 and 2020. So MEOS is a small satellite. It was the first one we designed in the CCDS, and it is a small satellite with a mass of less than 300 kilograms. And the aim of MEOS was to collect data on the lunar micrometeorite environment and also the radiation environment, as well as detect water, the presence of water and ice content on the lunar South Pole, with a view of developing a future moon base. The expected mission duration is slightly more than 2 years. On the other hand, NEOCORE, which was designed in April 2019, was a low-cost interplanetary mission involving up to 6 12U CubeSats, and that mission looked to estimate the relative position, velocity, and 2D shape of near-Earth objects. And that was expected to last 4 years and 8 months, utilising a low-thrust propulsion system. And finally, StrathCube, which is a project which is still ongoing at Strathclyde. It is a 3U CubeSat developed in support of an internal student-led project. Compared to what we will present today, that design concept has significantly changed, because this was essentially the first iteration of that we're presenting. It was originally designed with 3 objectives. So the first was to detect space debris in orbit. The second was a re-entry analysis looking at fragmentation. And lastly, one of the payloads which has now been dropped was wireless power transmission demonstration. And that had an expected lifetime of about 576 days. So the SSSD was, of course, used to generate the life cycle engineering results for each of those missions. And to facilitate this, firstly, a range of technical and procedural steps had to be put in place, and that included design model manipulation to cater for the life cycle engineering data, creating a data exchange interface between the SSSD and the design tool, and of course, looking at the overall performance. Secondly, we also will look at the results generated by this tool for each mission, and we'll present that in terms of absolute results, impacts per kilogram, and also looking at kind of environmental hotspots through single score and MCDA. And this was based, I would say, on the system boundary that was outlined by the ESA LCA guidelines. And lastly, we'll also look at the evolving behaviours and attitudes of participants towards LCE within concurrent engineering sessions as well. So one of the major technical and procedural issues was the inability of the design tool to host lifecycle engineering data. And this was because the design model's reference data library follows ECSS standards, and that defines the types of parameter that it can host. Unsurprisingly, the standard doesn't include typical lifecycle engineering parameter types within its metric system, which is problematic for this concept. So these problems were addressed locally in the Concurrent and Collaborative Design Studio by creating new parameters within the design model's reference data library for all the midpoint indicators and also the single score results, as well, as you can see in this table. The conceived data exchange interface is also outlined here, particularly the one on the right. In this regard, sustainable design is principally based on information provided to the decentralized design tool by other disciplines. So you have all these other disciplines which are feeding into this design tool. That information can then be extracted via a web service processor, and we call that element dynamic elements of the life cycle. And we'll come back to what that means in the next couple of slides. That can then be coupled with the life cycle inventory and also added to by static elements. So this might be elements which are not defined by the concurrent design session. So for example, if you're looking at design work, the number of work hours that goes into that won't be something that's calculated in there, but is very important to include from a life cycle perspective. And in that regard, you can then calculate the impact of the space mission to create life cycle sustainability assessment results. And these results can then be restored back into this database, either through a direct connection or through a domain-specific adapter with an Excel or JSON interface, for example. And once that is back into this, centralized database here, all the other disciplines can see that, and they can reiterate their design based on those results. Going to skip over this, we've kind of covered this already, but this is just the basic steps for applying life cycle engineering. So very quickly, it's identifying the sustainability challenges, gathering the skills that you need to do it, defining the baseline situation. Once you've got that, what are the hotspots? Redesign your space mission to try and reduce that impact. Looking at how those impacts actually then perform, and then once you've kind of concluded that, it's then a case of finalizing the approach and manufacturing your product. Now, in terms of how you apply this in the performance, like I say, you've got a difference between dynamic elements and also static elements. So you've got dynamic elements which are defined by mission-specific design data, but you've also got a lot of static elements which include elements that are not going to be covered. And this throws up a lot of questions about how you actually apply LC and concurrent engineering. So for example, should lifecycle engineering be treated as an independent discipline or part of system budgets? It could be argued as both. It's been applied as both in my experience. I think it sits somewhere in the middle because you can't really come to a full footprint until you know fully what the design is. In that regard, it follows the mass budget quite heavily. So for me, it sits somewhere between a discipline and a system budget. What do you do if you're missing potential data sets? Do you use an existing data set that's kind of close? Do you use a proxy, or do you do a very quick literature review and try and build a data set? How do you make design improvements? Do you replace potential impacting or very impactful components, or do you reduce the mass of those components? And what about the waterfall or burden shifting effects of that choice? So again, if you reduce the size of a component, does that shift the mass balance? Does that actually cause your impacts in other environmental media to increase or decrease? So it's very important to understand the full picture of an eco-design decision. And this is what I mean by static versus dynamic elements. So the light green here is your dynamic elements. So these are the elements that are influenced, but then you're looking at a space mission through the concurrent engineering. But you can see the vast majority in the darker green here are elements that won't be defined by that through that concurrent engineering session. So this is information you as the discipline expert will need to know or need to input yourself. So these are the absolute results of each of the space missions. Generally speaking, if you looked at them, it would indicate that each mission has generally improved, but in that regard, that's not exactly true. I mean, you can see Strathclyde does perform better across all 12 impact categories, but actually, when you look at them per kilogram, it actually looks very different. Now, I would argue that looking at them in terms of both of those approaches isn't a very good comparison anyway, because they're fulfilling different functions, if you like. But what this actually shows is that it's an added importance that has to be placed on how results are reported or communicated. A particular hotspot, I would say, amongst all three of those missions, however, was the use of germanium as a substrate within the solar arrays. And that was found to be quite impactful across human toxicity, mineral resource depletion. For human toxicity, it was mostly due to arsenic, mercury, and dioxins being released to air from the production and manufacturing process, while for mineral resource depletion, it was particularly because germanium is a listed critical raw material. But also ozone depletion was also an impact because of radical emissions in hydrogen chloride that was released during the launch event as well. So it should be noted that I would say the majority of well, the way I'll put it is, generally speaking, launchers would dominate small sat missions if a kind of share of emissions approach had not been set up. So in that regard, Neocore, the impacts were mainly driven by the launch event because a dedicated launcher was used, but in MEOS and Strathcube, a piggyback option was used, so they got a proportion of the launcher impacts allocated to those space missions. And when we look at this through a single score perspective, what we can actually see is that costs, maybe unsurprisingly, produced the highest share of the sustainability score of all the sustainability dimensions. But it's very important to realize that weighting adds sensitivity. So what you can see here is you've got on this row here a new multi-criteria decision analysis criteria and an old criteria at the bottom. All that was changed was one number, and it was the costing normalization from EU taxation to EU expenditure on space activities, and that has completely flipped the results. So essentially what I'm trying to say here is that you have to apply a single score with caution, because one small change can severely impact the results here. So again, it's less scientific than looking at them, say, as this, which is more a more scientific way of looking at them. The problem you've got here is very simple, that there's a lot of impact categories and there's a lot to focus on. So during concurrent engineering, it's not maybe the best approach, and we'll come back to that just in a second. But in terms of behavioural evolution, the MEOS study was used as a test case for the operability of the SSSD, and as such, the LCA results were used to inform the life cycle impacts. It was not a design driver. It was actually applied retrospectively, if anything. But during the Neocore study, there was clear evidence that discipline experts were proactively contributing to lowering the sustainability impacts. For example, one suggested switching the AOCS propellant from argon to AFM315E, which is a high-performance green propellant. It wasn't going to make any difference, but it was, again, an example of being proactive. And Strathcube, that had life cycle engineering as a mission driver. It was unclear, I would say, whether that change in participant behaviour was because of the reputation or the growing reputation of life cycle engineering, society's perception, or maybe even the fact that the mission itself had some sort of sustainability goal, but it does highlight that there is a growing awareness around the importance of sustainability issues amongst engineers. Now, just to kind of conclude with some final thoughts, I think it's very important that if you are making an environmental claim, you follow a standard methodology, and that is really re-emphasised in the European Green Deal. A communication recently came out saying that companies making green claims need to substantiate that against a standard methodology. That's exactly what this looks to do. Is it going to become more significant in the space sector? Well, there is a pressing need to include environmental considerations into the technical and economical analyses. It's already a requirement within Copernicus and Galileo missions. Ariane 5 used the approach to redesign their Ariane 6 launcher, and it could become an important part of the procurement process at ESA in the future. More research, of course, is needed to fill fundamental gaps in knowledge. Moving towards life cycle sustainability assessment, it's maybe a little too early for that yet. There is interest gathering. It's particularly social impacts are not very well defined yet, not just at a space level, but generally with the approach. So really, until a lot of these issues are actually addressed, it's unlikely that the space sector will transition to this just yet, but it is something that is certainly up and coming. And in terms of the integration of this approach to concurrent engineering, it's really important not just to go to the next step. So it's important we understand our impact, yes, but this is the next step to actually address that impact. Now, like I said, the reason we've got single score in here is really to try and reduce the learning curve of engineers, because it avoids them from focusing only on impact categories which they are familiar with. The problem is that it does add subjectivity, and it is not the most scientific method of analysis. But there is interest in maybe not MCDA, but life cycle engineering generally, such as at EPFL and you guys over in Switzerland. Or do we just need to completely rethink how we do space? So how we address that social foundation without breaching ecological ceilings. So a good example of that is if we look at the IADC guidelines, which looks at re-entering spacecraft in orbit. The social foundation would be supported because the goals of the space mission looks at addressing that social foundation. The spacecraft is deorbited, so it gets out of the way, so it basically lessens orbital space depletion and avoids space debris. Again, a massive tick there. But that action actually pollutes the upper atmosphere with metallic compounds and also the burning of electrical equipment. So that increases pressures on the climate and ozone boundaries. But indirectly, what it also does is it loses that resource. So it increases pressure on the social foundation and also other impact areas like land conversion, biodiversity loss, to create new virgin materials for future space missions. So my question here is that actually managing the issue, or is it just replacing one problem with another, or potentially several others? And that's something that life cycle engineering looks to try and address. So just to conclude now, life cycle assessment, eco-design, life cycle engineering, they're all very important tools. The interest in these tools are particularly increasing within the space sector quite rapidly, and their systematic integration into concurrent engineering is definitely an area that we need to kind of start exploring a bit more intensely. I think they're going to become a standard part of the space mission design process, particularly in Europe in the next decade or so. And I hope that that evolution will eventually also include life cycle engineering so that we can look at a wider sustainability impact rather than just focusing on the environment as well. I think I'm just about at 45 minutes. I just want to thank the University of Strathclyde and Metasat UK for also assisting in compiling this presentation, and I'm happy to answer any questions that you may have.
Yeah, thank you, Andrew, for this nice presentation. And indeed, I see also that it's getting more and more attention everywhere, also here for the students who might be watching this later on YouTube or who might be now in the audience. Also here at EPFL, we're also looking at it more and more, as you had it on your slide, because we have this concurrent. So originally this talk was supposed to be for the concurrent engineering class, but we decided to make it a bit broader and for everyone, to make it available for everyone, because we think it's relevant nowadays. But in our class of concurrent engineering, we actually want also to implement sustainability and life cycle assessment. So these topics are very relevant, and I think also at ESA LCA, for example, at their CDF, they might maybe in the future also use it, hopefully. So yeah, I think it's a very timely presentation, or very relevant nowadays. But I think it's now time for the questions. If anyone has any questions, I have written some down here, but I just want to leave the floor to the people maybe in the room. Have any questions?
Yeah,
yeah.
Question.
Oh, yeah.
Thank you. So first of all, thank you for the presentation. It was really interesting. And I have a more practical question. So I'm a member of the EPFL spacecraft team.
Yep.
We're developing a CubeSat to study the upper atmosphere, so the gas composition of the upper atmosphere. And for our mission, we would like to apply an LCA methodology and like applying it with a single score that has also been developed by students. And my question was about the data set. So one of the most difficult thing when you do LCA is to know where to find all the data that you need. And as you mentioned, ESA has some very good data set available. Is it also available for students? How can someone access this kind of database? Is it hard? You need to have a project in collaboration with ESA. So this kind of information.
So yeah, again, I don't want to speak on behalf of ESA, but my understanding of their process is virtually identical to accessing the Strathclyde Space Systems database. So again, to access the ESA one, you need to be in an ESA member state, I believe. For the SSSD, you don't have to be in an ESA member state, so that restriction's removed. But what you need to do in parallel is have an Ecoinvent license. So you need to send a request. Let's start with the European Space Agency. You need to send a request to the Clean Space team. You need to be able to prove you have an Ecoinvent license existing because they've built their database on top of Ecoinvent.
Okay.
And assuming you fill those requirements, they will allow you access to the database. Now, on the SSSD, that is now managed by Metasat UK. So you send an email to me at Metasat UK. Again, It's the same process. We need to see that you have a valid Ecoinvent license. We don't have the restriction like ESA that you have to be an ESA member state. You can be anyone globally. And again, assuming you fill that requirement, we can send you access to the database. Now, just because you would have access potentially to both databases, does not necessarily mean that when you do apply this in a concurrent engineering environment that you're going to have every data set you need. In fact, I've not actually done a concurrent engineering session where I've had every single data set, because quite often you'll have very unique components or systems that are built for a particular space mission. And then that's kind of what I alluded to there. What do you do in that situation? Do you use a proxy? Do you do a literature review to try and find out what the impact would be? It becomes very difficult, and particularly because in a concurrent engineering environment, it's time constrained. So you don't necessarily have the time to be spending doing a literature review. So it can be quite difficult. Okay. And again, that's just I would just very clear for the ESA stuff, that is just my understanding. I don't want to talk on behalf of ESA.
Yeah. Thank you.
Maybe a small thing I can add to what Andrew just said. I think recently ESA has, you don't necessarily nowadays need to send an email to ESA anymore, but they have this website, I believe, if you from the latest presentation at the Clean Space Industry Days.
I wasn't 100% if that had been implemented yet. That was certainly the approach we were going for. If it's been implemented, my apologies, then that's how you do it. But
yeah, we weren't sure either. It has been, I know a colleague of mine did try it that way, and I think it worked. So yes, I think it has been implemented. But otherwise, sending an email is always the backup option.
Yep.
I see that. If you have do you have another question?
Maybe just one other question,
and then or Lawrence also has a hand raised, but maybe you can ask your question
first. Just very quick. What is an Ecoinvent license?
So Ecoinvent is essentially the world's most widely used lifecycle assessment database.
Okay.
When ESA and also I were developing our databases, we couldn't build something completely from scratch because, for example, if we were going to use electricity consumption in a process, I wasn't going to go and measure the environmental impacts of the electricity grid in Germany or Norway, for example.
Okay.
So it's been built on top of that. So it's an existing database that is a commercial database.
Yeah. Mm-hmm. Oh, okay. Okay. I read in the chat that EPFL has an Ecoinvent license, and that's very interesting. Yeah. Thank you.
Lawrence, I asked you to unmute, so I guess you can unmute yourself.
Yeah, can you hear me?
Yes.
Yeah, first, Andrew, a fantastic presentation. Thanks a lot for that. As you said, it's super relevant, and I'm excited to see that there's a presentation on that and people looking at this topic. Now, first question, and I apologize if you mention it, but so you applied the LCA during the concurrent engineering session, at least for one of the 3 case studies.
For 2 of them. So we applied it retrospectively for MEOS, but for Neocore and Strathcube, it was in real time. Yes.
Okay, and were you or let's say an LCA expert kind of the subsystem lead on this, or were you able with the tool you presented to give that let's say power to the systems or subsystems expert?
So during Neocore, I acted as the eco-design discipline expert, essentially. So I was a different kind of subsystem, and we had a different system engineer. But what I found in my experience in that session was I was having to work very closely with a systems engineer. And the reason for that was because the way it worked was I had to very kind of closely follow the mass budgets. Now, that doesn't mean that I didn't have to go and talk to other people, because I had to go and talk to the power subsystem, the thermal subsystem, etc., etc. And generally, the process we developed there allowed that to kind of run quite smoothly, but it was still quite a lot of labour to do all that. So when we did the second study, which was Strathclyde, we then trialed it as part of a system budget, if you like. So I worked more closely with the systems engineer and essentially acted as system engineer and ran eco-design almost as a kind of discipline system budget hybrid, if that makes sense.
Yeah.
And I think that worked fairly well, because for me, I don't think the discipline is a true discipline, but I don't think it's quite a systems budget either. It's somewhere in the middle.
Okay, I see.
But the process that we defined for it, it did work kind of, well, we're not going to say flawlessly. There's, of course, improvements that could be made to it to make it a bit more seamless and to have a little less labour, but it did work, and we were able to input, let's say, lifecycle engineering results to the database, and people were starting to make improvements based on the results. I hope that kind of answered your question. If not, then
no, that's very, very good. Thanks a lot. I have a couple of questions, but I don't want to steal anyone else's question.
No, I don't see for now anyone else's hand raised, so I think you can go ahead with your question.
From a tool perspective, do you feel there is a need for let's say, generalized, let's say, add-on to Comet you mentioned, or something similar to make that process easier?
I don't necessarily think it's so much an add-on to Comet. I think it's more to do with how the data is extracted from Comet into the lifecycle engineering tool. I think that there, so I don't think that's a Comet problem. I think that's more the lifecycle engineering tool problem. And through my company, we are looking at that at the moment. I also think that, I mean, we've also got kind of workbooks that we've developed specifically for lifecycle engineering, but because Comet essentially follows, or the reference data library follows the ESA standards, what has to happen for any concurrent engineering facility is they need to create the environment within the tool to be able to receive those results, which is what we had to do in our studies. So again, if there was like parameters, let's say, for lifecycle engineering, that would be a bonus and it would save an additional step. But at the minute, that's not present in the reference data library. But that's more because the ECSS don't define those as parameters.
Okay, I see. Thanks for that.
Mm-hmm. Thanks, Lawrence, for your questions. Do you still have another one left, or feel free?
If I have time, of course. I don't want to steal.
Well,
one last.
Thanks. Yeah. So as you mentioned, I think at the beginning, early stage, you don't necessarily have the knowledge not only on how your spacecraft would look like, but also how the whole, let's say, AIT process is.
Yep.
First of all, it's also not necessarily common in concurrent engineering to have those expertise. So how did you a bit juggle that, or did you assess that?
Okay, so one thing I'll say is that doing LCE doesn't mean that you shouldn't also continue to do a life cycle assessment further down the field. But in terms of specifically doing it at that stage, there are, of course, areas that you're going to have to do, let's say, expert judgment on. For example, number of work hours that go into phase A, phase B, phase C. And how that worked was actually in collaboration with the European Space Agency. So I had a lot of proxy values for a typical, for example, Earth observation mission, science mission, all these different kind of parameters. So we could essentially do well-judged predictions. But it's very important to know that when you're doing an eco-design, you're essentially predicting the future. So no measurement is going to be 100% accurate. You're going to be more accurate later into the design that you actually go. But as I say, you've got less scope then to actually try and reduce the impact. So what I would say is that for me, I handle it by evidence-based and well-judged predictions, but use that to kind of guide eco-design principles going forward. So how do we reduce that impact, and how do we make sure that if that is a major impact, that doesn't actually remain like that, we can kind of change that. So again, I would say until we get to kind of maybe the end of phase C, you're not fully going to know the real environmental impacts, but it's a prediction to try and mitigate those before they occur, essentially.
Okay, I see.
Yeah, thank you.
Thanks a lot. Huh?
My pleasure.
Connie and Andre, if it's fine, I just want to squeeze in one last question.
Yes.
Tiny one.
One last time.
Thank you. I was just intrigued by on your slide where you had findings from your different missions that you looked at. I think you said in NIACOR mission, I think it was the second one, right? That you saw that someone proactively decided to, for example, swap the fuel or the propellant.
Yes.
Used. It's more of a bigger picture question. How you already kind of said that you implemented life cycle assessment already in that mission, kind of, but nevertheless, you noticed that people proactively begin taking into account sustainability. Yeah. I'm wondering, because the big criticism against life cycle assessment at very early stage design is that everything is not set in stone and there is so much uncertainty. So you saw people doing proactive implementation of sustainability. How is life cycle assessment needed to get people's attention to do sustainability? And I don't know, do you see where I'm going at?
Yeah, I think
But
for me, I think part of that was, of course, this was done in-house at the University of Strathclyde. I'd been working at Strathclyde at this point for about 4 years or thereabout, maybe slightly less than 4 years. So people knew of my work. So again, you could argue there's bias there because they went, oh, let's try and contribute to the work of myself. But that was the first time I really noticed somebody trying to, let's say, do something. But if you go on to Strathcube, what was very interesting about that was the inclusion of life cycle engineering was actually specifically requested by the customer, which was a set of, so we have student societies, and it was a student society who wanted to do this mission, and they, without knowing who I was, actually came in with that requirement that they wanted to actually do this, which was actually very, very interesting for me. Now, they didn't know at the time that actually Strathclyde had set life cycle engineering as a requirement in all concurrent engineering studies at this time. They didn't know that. But the fact that this request had actually come in was very interesting to me, and I don't think it was anything to do necessarily with the work I was doing. So whether that's just that they are becoming more aware of space sustainability issues, I'm not entirely sure.
Yeah. Okay. Interesting. So it's okay. So to make people more proactively get into sustainability, would you say it's a matter of having someone authoritative saying that sustainability needs to be taken into account, or is it more about just promoting the fact that sustainability, getting them aware of sustainability?
I think it's very important to let them know you're in the room. I don't think forcing something upon them is necessarily the best approach, because not everyone's going to necessarily be able to have the same degree of flexibility to improve the design. the way I do it is that when I do my initial assessment, I can come up with a set of hotspots. So, for example, if I found the power, maybe let's say the solar arrays were a hotspot because of the use of germanium, I can go and have a specific dedicated conversation with the people from power and say, look, is there any way you can find a different solar panel that achieves the same purpose, and try and replace that component to lower that impact. So again, that's one approach you could do, but in terms of actually saying, trying to get them to be a bit more proactive and come to these conclusions themselves, make them aware. We sometimes had presentations in kind of off days, if you like, and kind of pressing upon them the importance of this and why it's important. It can sometimes make them think a bit more about these kind of things, but there's no, let's say, at least in my opinion, there's no particular way that you're going to motivate them. It's very situationally dependent.
Okay. Yeah. Okay, thanks. I think that's food for thought for us, and then maybe also for at ESA or at other bigger CDF places if they want to implement this. But yeah, thank you, Andrew, for all the time to give this presentation, and thanks for everyone following it live and then watching it later on YouTube. So yeah, this was recorded, and so it will be placed on YouTube soon. If interested, you can send me an email and I can send you the link afterwards. But yeah, thanks everyone for being here. And yeah, see you at our next seminar. So you can follow us go to our website, the eSpace at EPFL, and you can see the seminars going there.
Thanks,
Super,
Andrew.
thank you very much.